Okay, so the mean value theorem has to do with the slope of the secant line, slope of the tangent line, so derivatives. But what goes hand in hand with the mean value theorem is also this thing called the intermediate value theorem. Okay? It says if f is continuous on a closed interval. So part of this is just learning how to read these theorems. As you get into higher level math, you're going to see a lot of theorems. And at first, when you read them, you're like, what the heck did that just say? So you've got to figure out what this math language is saying. And that takes skill. That takes time to learn. All right, so here's the intermediate value theorem. If f is continuous on a closed interval from a to b, let's graph something like that. So from a to b, we have some function that is continuous on that interval. Does it state anything about differentiable? No, but we have to be continuous. So what does that mean? Can this function have a cusp, for instance? Yeah, a cusp is continuous. This theorem says nothing about being differentiable, so we could have a cusp. Okay, I'm not going to necessarily draw a cusp. I'll just draw some function. I'm just going to draw some curve like that. Okay, do you agree that my curve is continuous on the closed interval from a to b? Yes? Okay, it could also have a cusp. It could also have a vertical tangent line as long as it's continuous. Okay, now let's read the rest of the statement. And k is any number between f of a and f of b. Okay, let's talk about what f of a and f of b are. F of a and f of b are the y values here. So here's f of a, here's f of b. So they're saying choose some k in between f of a and f of b. Now I stated the word inclusive. That means can it equal f of a or f of b? Yes. Okay. I'm not. I'm just going to choose some k in between. Okay, so everybody following how I'm writing all this out? We have some function that's continuous. We've chosen some k, some y value between the y values. Then there's at least one number c in the closed interval such that f of c equals k. Okay, cool. What does that mean? So if I take this, do you see how that y value, there's a corresponding x value inside the interval from a to b, yes? Okay, there actually might be another one over here. There might be one here, and there might be one here, but there's at least one, correct? Now you might be like, what is this all about? Like, I mean, duh, right? If I have a y value, I've got an x value in the interval, right? It's actually a huge theorem. When you get into math, things get really nitpicky. So all it's saying is if I choose some y value in between my y values, then that's going to correspond to some x value in between the x values. Okay, it's that simple. What, however, this is used a lot for, and if you want to go back to historical math here, what this is used a lot, this is used a lot to prove there is a zero of a function. So think before calculators, think way, way back when, and they're trying to find zeros on these graphs. Well, if I can prove, I can't, let's say I don't know where the zero is, but I can kind of hone in on the zero. And let's say I found some value that I know the y value is negative. And so let's say f of 2, the y value is negative. Let's say f of 3, the y value is positive. And I know that my function is continuous. What must there be? There must be a zero between 2 and 3. Does that make sense? Right? So let me state that. So let me give you an example. Given f of x is continuous and f of 2 equals, I don't know, -1. And f of 3 equals, I don't know, +2. If that's the information that we're given, we have the condition that function is continuous. We're looking for a zero. So think of the k value as 0. Is not 0 between -1 and 2? Right? My y values of -1 and 2? Yes. Since my function is continuous, what the intermediate value theorem says, then there must be at least one value in between 2 and 3 such that that f of c equals 0. Let's talk about how to actually state that. So given that f of x is continuous and we have these two values, by the intermediate value theorem, and what's nice in calculus, we can use IVT for short if you're going to use this theorem. There exists a 0 in the interval from 2 to 3. Does that make sense? Like such that f of c equals 0. No, there exists a c. I'm sorry. There exists a c, some x value between 2 and 3, on the interval from 2 to 3, such that f of c equals 0. My bad. You can start to see where the language gets really kind of difficult to state, right? It's a very simple concept, but sometimes it's difficult to communicate that mathematically. So I'm going to pause right there. Does that make sense how I've given you that example? Okay. Does that have anything to do with the derivative or slope or anything like that? Not at all. Okay. So now let's state the mean value theorem. So at first, they might look very similar, but they're not. So the mean value theorem, we've restated this from our previous page, but we're going to draw a picture again for this. Let f of x be differentiable, remember, on the open interval and continuous on the closed interval. So let's draw that same graph really because it matches that. Well, I'll draw something like that. Do you agree that that function is differentiable on the open interval and continuous on the closed interval? Yeah. If we know it's differentiable and continuous, then there must be at least one point inside that open interval such that the slope of the tangent line at C is equal to the slope between A and B. So if I draw the slope of the secant line, so this slope is equal to f of B minus f of A over B minus A. Do you see how there's some point somewhere between A and B, we'll call that C, such that f prime of C equals the slope of the secant line? We good with that? Any questions? I know this is very theoretical, very conceptual. It's very mathy, very pure math. But we're going to get some examples next. Now, I want to also give a disclaimer here. This whole unit is not a bunch of theorems. This is really the heavy theorem day. After this, we'll see like one more theorem, but this is heavy theorem day.